Hi everyone. Today we will talk about a very interesting concept of transfer of heat but by radiation. Last time we discussed transfer of heat by conduction. Remember, conduction requires a medium like a conducting rod. But the heat transfer by radiation does not require any medium. Now in radiation we have three major topics: Stefan's law, Wien's displacement law, and finally Newton's law of cooling. So let's discuss briefly the concepts and the formulae in these topics. Let us see what is Stefan's law. Imagine you have a hot body whose temperature at time small t is capital T. So capital T is the temperature at a particular instant. Let us assume the surrounding temperature is very low, approximately 0 Kelvin. Then this body, being hotter body, will emit radiation, right? The energy of the radiation per unit time, this is also called your power, right? So power is energy emitted per second. So energy of the radiation emitted per unit time according to Stefan's law is directly proportional to the area, or this A is the surface area of the body. So surface area of this body. Okay. Capital T to the power 4. So you need to remember that the power is 4. Okay. Now this formula, which is Stefan's law, can also be written in this way. Energy per unit time can also be called as power, isn't it? So this is the thermal power of the radiation emitted by the hot body, which is proportional to surface area of the hot body times temperature of the hot body power 4. Okay. Now this formula for a black body becomes P equals to some constant will come, right? Whenever proportionality becomes equal to, we put a constant of proportionality times A T power 4. This constant is called Stefan's constant. Okay. Now this is how we write the formula for a black body. So P represents the thermal power emitted by a black body. Now what is the definition of a black body? A black body is one that absorbs all wavelengths of light when it falls on it. Similarly, if it is hot, it will emit all wavelengths of light from 0 up to infinity. Okay. Now real bodies like Pankaj sir or this marker, we have not black body, right? So for us, how the formula will change? So for other bodies which are not black bodies, the formula is written as thermal power equals to some constant E which depends on the body itself times sigma, the Stefan's constant, A T power 4. So just remember to put this extra constant which depends on the body, and this E is what we call emissivity. Emissivity. Now in problems where they mention black body very clearly, then you can use directly this formula, where emissivity of a black body will be how much? Obviously 1, because by putting E equal to 1 you will get this formula, right? So for black bodies emissivity will be 1. For other bodies, okay, emissivity will be given as some number. Now this formula is applicable when the surrounding temperature is assumed to be 0 Kelvin. But in reality, there will be some surrounding temperature, yes or no? In that case, how the formula will be written? So if surrounding temperature is, let us assume T0, then the formula for power emitted by a body is equal to E sigma A T power 4 minus T0 power 4. So this factor you must include if the surroundings temperature is not negligible. If it is, let us assume surrounding temperature is 27 Kelvin and the temperature of the body is as much as sun's temperature, then compared to sun's temperature, the surrounding temperature can be neglected, isn't it? So in such cases you can forget about this number. But if they mention very clearly in the question that surrounding temperature is not negligible, then you should use this formula. The minus sign, why it is there, is very easy to understand. This is the formula for power emitted by the body. Now, due to the temperature of the surrounding will also emit radiation. So, this much power will be emitted by the surrounding, and some part of that radiation from the surrounding will be absorbed by the body. So, now the body emits power, at the same time absorbs power. So, this is the net power emitted by the body. Net power emitted by the body. Okay, so if the surroundings temperature is less than temperature of the body, then body will emit more radiation than whatever it absorbs. So you have to subtract whatever you have emitted with whatever you have absorbed. For example, if you emitted 100 joules of energy per second and you absorbed 40 joules of energy per second, so you emitted 100 joules, but from surrounding 40 joules came to you. Then how much will you emit? Total 100 minus 40, right? So that's why we must subtract these two terms. Okay. Let us now discuss Wien's displacement law. Imagine I take a spoon which I heat it nicely on a furnace, like your flame. After heating the spoon nicely, let me take the spoon in a cooler environment. So once you take it in a cooler environment, it will emit radiation, right? Now that radiation, if you pass it through a prism, that prism, what it will do, as you know from your school days, right? The prism will separate the frequencies or the wavelengths. So that is what we call as spectrum. Now, if you look at the spectrum, you will find that some colors will be more bright and some colors will be less bright. So you can plot a graph between color and brightness. However, we will give technical name. So for color we use the word wavelength, and for brightness we use the word intensity. So if you plot a graph of the radiation emitted by a body at some temperature capital T, let's say. So T is the temperature of the body at which it is emitting the radiation. So that time you will find that the graph looks something like this. So you can see the intensity, the y-axis, has a maximum, right? Has a maximum I max for which wavelength? Some wavelength, and that wavelength I am calling lambda m. So lambda m is the wavelength at which the intensity, or I can say the brightness, is maximum. So remember, lambda m is not the maximum wavelength. Lambda m is the wavelength at which intensity is maximum. Okay. To understand the relation between the wavelength lambda m at which intensity is maximum and temperature. So to know the relation between lambda m and temperature, think of this. Imagine you iron your cloth. So when you iron your cloth and you go near the cloth, you will feel some radiation coming or not. That radiation is what is infrared, IR rays. Okay. Then if you increase the temperature of that body, if you keep increasing the temperature, you will see red color will be emitted. If you further increase the temperature, yellow color will be emitted. So what did you realize? As you increase the temperature, the radiation goes from infrared to red, then yellow, and then later on it will become more violet. However, by the time violet is emitted, all these colors will reach your eyes. So it may appear as white, though it should be actually violet. But by the time violet reaches your eyes, all these colors have also reached, and your brain will remember that for some time. You will see the color as white. So as you increase the temperature, this is how the wavelength changes. Now, I hope you all know that red has larger wavelength, violet has less wavelength. So what does that mean? It means as you make the body more and more hot, it starts emitting colors which have more frequency, or I should say less wavelength, right? So with increase in temperature, the wavelength of the radiation decreases. So, is it correct to say a body at temperature T emits only one wavelength? No. A body at temperature T emits many wavelengths. But we see that color for which the intensity is maximum. Okay. So, as we increase the temperature, the wavelength at which intensity is maximum, that wavelength lambda m will decrease because wavelength of violet is much smaller than wavelength of red. So therefore, what we learned is the wavelength at which intensity is maximum is inversely proportional to temperature. Now, when you remove the proportionality and make it equal to, a constant should come, right? So that constant we write as W and we call it obviously Wien's constant. Okay. Let us see some interesting questions now. A spherical black body with radius of 12 cm radiates 450 watt power at 500 Kelvin. If the radius were half, so radius is half and temperature is doubled, the power radiated would be how much? So let's analyze the question. This is the initial condition. The radius and the temperature of the black body is given, and this is the thermal power emitted or radiated by the black body. They have decreased the radius to half and the temperature is doubled. They want us to calculate the new power. So here obviously we are going to use the Stefan's law. So for black body, how do you write? Sigma A T power 4, right? So for new case divided by old case, so this is the final and this is the initial. Sigma is constant, so in the ratio it will cancel. So A dash by A, T dash by T, but power 4 is there, so temperature power 4. Now, since they have mentioned radius and not area, we have to use the formula for area of a sphere because the body is spherical, they told. So spherical body, what is the surface area? 4 pi r square, right? So this A dash can be written as 4 pi r dash square divided by 4 pi r square into T dash by T power 4. 4 pi cancels. Now they mentioned the radius is half. So new radius will be half times old radius, right? Divided by r whole square, isn't it? So this is r dash by r whole square and r dash is half times r and t dash is 2 times t. So 2 times t divided by t. So t gets cancelled, r gets cancelled, half square will be 1 4 and 2 power 4 will be how much? 4 times 4, isn't it? So 1 4 will cancel and that will be equal to 4. So if you cross multiply, what we will get? So from here we see that p dash by p is 4. So if you cross multiply, p dash will be 4p. What was the initial power? Initial power was 450. So this will be 4 zeros are 0, 4 5s are 20, 0 2 carry, 4 4s are 16, 17, 18. So the answer is 1800 watt. Let's see the next question. It says a black body is at a temperature of 2880 Kelvin. The energy of radiation emitted by this body with wavelength between 499 nanometer and 500 nanometer is U1, between 999 and 1000 nanometer is U2, and between 1499 and 1500 nanometer is U3. They have given you the value of Wien's constant. We have to check which options are correct. Now they have given the temperature of the body and Wien's constant. So obviously we are going to use Wien's law. So Wien's law says the wavelength of the radiation at which the intensity, or I can say energy, because energy is proportional to intensity only. So the wavelength at which your energy emitted is maximum is inversely proportional to temperature, right? So if I write equal to, we write the constant as Wien's constant. So if you substitute 2.88, I can write 288 by 100 into 10 power 6, right? So this is your Wien's constant divided by temperature is 2880. So this can be cancelled with this. 10 will be there, 102030. So 1000 in denominator will cancel 1000 here. So you'll be left with 1000. Unit will be what? This is nanometer Kelvin, right? Nanometer Kelvin divided by Kelvin. So the unit will be nanometer. So what did we learn? That at this wavelength 1000 nanometer, which is in this range, your energy U2 is maximum. So we came to know U2 is maximum, and if U2 is maximum, others should be less. So U2 should be greater than U1. So the right answer should be option D, right? Let's see the next question. It says two spherical bodies, A radius 6 centimeter and B radius 18 centimeter, are at temperatures T1 and T2 respectively. The maximum intensity in the emission spectrum of A is at 500 nanometer. So this is the wavelength at which your intensity is maximum. So this is your lambda m, remember, but for body A. And in that of body B, it is 1500 nanometer. Considering them to be black bodies, what will be the ratio of the rate of total energy? Rate of total energy means power, right? Power is energy emitted per second, radiated by body A to that of body B. Here is the given information. For body A, the radius is given as 6 centimeters, so it is a spherical body. Temperature is not given as a number, but it is given as a symbol T1. And the wavelength at which the intensity is maximum, which I usually write lambda m, but here two bodies are there, so I wrote lambda m for body A as lambda A and lambda m for body B as lambda B. So these are also given. We need to find the rate of energy emitted ratio. The rate of energy is nothing but power, right? Thermal power in this case. So what was the formula for power of body A? Sigma area of body A, temperature of body A power 4, and here also sigma area of body B, temperature of body B power 4. Now why emissivity I did not write? Because they are told in the question the bodies are black bodies, so no need to write emissivity, because for black body emissivity is 1. So sigma gets cancelled. Now they are spherical body, so area can be written as 4 pi radius of A square by 4 pi radius of B square into TA by TB whole power 4. 4 pi also gets cancelled. Now temperatures are not mentioned, but wavelength at which intensity is maximum, that they have given. Now here we need to also use Wien's law. So if you apply Wien's law, the wavelength at which intensity is maximum is equal to Wien's constant by temperature. That means if you take the wavelength of body A, not wavelength of body A, wavelength of the radiation emitted by body A, where intensity is maximum, that wavelength for body A divided by wavelength for body B will be, since it is inversely proportional, it will become TB by TA. W will cancel. So in place of TA by TB, if I do ulta here, reciprocal, if I take TA by TB, I will get lambda B by lambda A, isn't it? So since the ratio of temperature they have not given, but wavelength they have given, let us substitute for TA by TB as lambda B by lambda A. So I will get RA by RB whole square into, here I will get lambda B by lambda A power 4. So what is the radius of A they told? 6. Here 18 power 2, and this lambda B is 1500 divided by lambda A is 500 power 4. So 6 3s are 18, right? So 1 by 3 whole square will be 1 by 9 into 00 cancel, 5 3s are 15. 3 into 3 into 3 into 3. 4 3s will be there. This 3 and 9 will cancel, so the answer will be 9. Right? A simpler way to solve this problem without writing so many things is by using the concept of proportionality. So we know for a black body, the power emitted is proportional to its area and temperature power 4. Here radius is given and we know area is proportional to radius square for a spherical body. Temperature is not given, but the wavelength at which intensity is maximum, that they have given. And we know that wavelength and temperature are inversely proportional. So I can write this as 1 by lambda, isn't it? So now see what happens. From here to here, the radius has increased 3 times when I go from body A to body B. That means for body B, the power will increase because of this radius. Remember, from here to here, radius increases 3 times. So the radius square will increase 9 times, isn't it? Now, what about wavelength? From here to here, the wavelength has also increased 3 times, right? 1500 is 3 times 500. So now if wavelength increases 3 times, 1 by wavelength power 4 will become 1 by 3 power 4 times. So the power of B will be this many times power of A. And 3 power 4 is 3 power 2 into 3 power 2, right? 3 power 2 into 3 power 2. 3 power 2 and 9 can be cancelled. So this will be 1 by 9 times power of A. So if you cross multiply this 9 here, you will get power of A divided by power of B as 9. Right? Let's see the next question. Here, more than one option can be correct. It says two bodies A and B have thermal emissivities of 0.01 and 0.81 respectively. The outer surface area of the two bodies are same. So the surface area is same. The two bodies emit total radiant power at the same rate. The wavelength lambda B corresponding to maximum spectral radiation. So this is the wavelength at which the intensity, the radiation is maximum. In the radiation from B is shifted from the wavelength corresponding to maximum spectral radiation in the radiation from A by 1 micrometer. So basically what they are saying is the wavelength at which intensity is maximum for one of the body is shifted from the other wavelength by 1 micrometer. If the temperature of A is 5802 Kelvin, they want you to find and check the options which are mentioned here. Okay. So these are the given informations. For body A, emissivity is 0.01. For body B, it is 0.81. Areas are given same. Temperature of body A is 5802 Kelvin. We have to find temperature of body B. Also, they told the wavelength at which the radiance is maximum, the wavelength at which the intensity is maximum, that wavelength for the two bodies differs or shifted by 1 micrometer. And we have to find the wavelength of the radiation emitted from the body B at which intensity is maximum. Now, this is the most important part which you need to catch from the question. They also told the two bodies emit power at the same rate. So they should say emit energy at the same rate. So if they emit energy at the same rate, what does it mean? It means thermal radiation emitted per second or per time is same. That means power emitted by the body A is equal to power of radiation emitted by body B. What will be the power emitted by body A? Formula was emissivity, Stefan's constant, surface area, temperature of A power 4. This will be emissivity of body B, Stefan's constant, surface area, temperature of body B power 4. Here surrounding they have not mentioned, neither they mentioned the surrounding temperature. So I am assuming surrounding temperature is very small compared to the given temperature. So the constants will cancel, right? And therefore you will get temperature of B divided by temperature of A power 4 will be equal to EA divided by EB, isn't it? So very carefully you check, okay, cross multiply once and check. TB power 4 is with EB. So if you cross multiply, TB power 4 will be with EB. Now emissivity of A is given 0.01, which I can write simply as 1 by 100, and this is 0.81, which I can write 81 by 100. So 100 by 100 by 100 will cancel. You got my point, right? This can be written as 1 by 100. This can be written as 81 by 100. So when you divide these two, 100 will cancel. So you will get 1 by 81. So this will give you TB by TA will be equal to 1 by 81 power 1 by 4. Isn't it? So now how to do this? Well, you should know 1 by 4 can be written as 1 by 2 again power 1 by 2. Isn't it? Right? So what is the square root of 1? Square root of 1 is 1 only in the numerator. But in the denominator, square root of 81 is 9. So this will be 1 by 9, right? Power, again this half is there, remember. Because actually the power is 1 by 4. So 1 by 4 I wrote 1 by 2, then again power 1 by 2. What is square root of 1? In the numerator 1. Square root of 9 in the denominator will be 3. So it will be 1 by 3, right? So we found temperature of B divided by temperature of A is equal to 1 by 3. So if you cross multiply, temperature of B will be temperature of A by 3. Temperature of body A was given 5802 divided by 3 here. So if you divide this, 3 1s are 3, 2 carry, 3 9s are 27, 1 carry 10, 3 3s are 9, 1 carry 12, 3 4s are 12. So this is the temperature of body B. Now we need to find the wavelength lambda B. Remember the difference is given. So this part is given, okay. Now we can use Wien's law. The wavelength of radiation where intensity is maximum for body A will be Wien's constant by temperature of A, right? And wavelength of radiation for which intensity is maximum for body B will be Wien's constant by temperature B. So if you divide these two, you'll get lambda A by lambda B is equals to TB by TA. Right? And already we found TB by TA as 1 by 3. So this is 1 by 3. So if I cross multiply, lambda B will be 3 times lambda A. Right? So now if I put this lambda B in this equation, right? So put this lambda B here. What will you get? So 3 lambda A minus lambda A equals to 1 micrometer. So 2 lambda A equals to 1 micrometer. So lambda A equals half micrometer. And once we found lambda A, you can substitute it back here. So lambda B will be 3 by 2 micrometer, which is also 1.5 micrometer. Right? Let's see a very interesting question. It says a sphere, a cube, and a thin circular plate of same material and mass. So material and mass are same, are initially at same temperature also. Which one will cool fastest? Now, if they say material is same, then it means density will be same, right? Density is same. If density is same, mass is also same, right? Therefore, volume of the three bodies has to be same because these three are related. Density is mass by volume. So if two numbers are same, the third number also has to be same, right? Now, what is the formula for heat lost per second, which is nothing but your thermal power, right? Power radiated. According to Stefan's law, it is EA T power 4. There is a Stefan's constant also. Now, observe carefully. E we can take same because the materials of the two bodies are same. And this heat lost per second, what happens to that heat lost? Because of the heat loss, its temperature will decrease, isn't it? So I can write heat lost according to the principle of calorimetry as mass into specific heat into the change in temperature. But since heat is lost, this change will be negative. So better to put minus. Are you clear why minus sign is there? Remember, when temperature decreases, final temperature will be less than initial temperature. So your change in temperature is always final minus initial, right? But since initial number is more than final, so less minus more will be negative. So please put this minus sign because the overall quantity, this whole thing should be positive. But you know delta T is negative. So this minus sign will make sure that this whole thing is positive, right? So heat lost has to be positive. We have discussed already. So this is the heat lost divided by time taken. Let us write delta T. So equal to sigma EA T power 4. Now, if I write this as minus delta T by delta T equal to sigma EA T power 4 divided by mass into specific heat. Now, this is nothing but your rate of cooling. So this is your rate of cooling, or I can say average rate of cooling. What rate of cooling? Average, because I wrote delta T. But when delta T tends to 0, the same thing can be also written as d capital T by d small t. Minus sign is just there to tell you that temperature decreases with time. Okay. So this is a rate of cooling. So according to this Stefan's law, what did we find? The rate of cooling is proportional to emissivity, area, temperature of the body divided by mass into specific heat in the denominator. But here the sigma will be constant, emissivity is same, mass is also same, right? And mass is same in the problem. Now if mass is same, specific heat is same, both will be same. Right, mass is same, specific heat is same. That means the whole thing is what is left, only area is different. Even temperature is same, they told. That means the rate of cooling is directly proportional to the area. So the one which has more area will cool faster, right? So now you have to decide out of sphere, cube and circular plate which has maximum area. Can you guess? Well, think about it. A sphere will have this kind of shape, right? It will have 3 dimensions. It will have. Cube will also have this 3 dimension. Now this is a thin circular plate. So one side the dimension is very small. But all the 3 should have same volume. Therefore, logically, if you think, this plate should have largest area in order to have same volume, isn't it? So logically, if you think, the area of plate, circular plate, will be maximum. Okay, if the volumes are equal, obviously volume should be same, otherwise you cannot say like that. So if volumes of the 3 bodies are same, then plate will have the largest area, and therefore whichever has the largest area will have the highest rate of cooling. Rate means how fast it cools. So therefore the answer to this question is thin circular plate. Now if you want to see mathematically why this one will have the largest area, then just mention in the comment section. I will give you a mathematical proof that circular plate will have the largest area and sphere will have the smallest area if the 3 bodies have same volume. Now let us discuss Newton's law of cooling. Newton's law of cooling gives the rate of cooling of a body. Rate of cooling means what? The rate at which temperature decreases with time. But why do we need Newton's law of cooling? Because already we saw in Stefan's law, it gives you the power radiated, right? In terms of surface area, emissivity, temperature, power, 4 of the body. So using that power lost, we can write it as energy lost per unit time. And energy lost can be written as mass into specific heat into change in temperature. So we can calculate the rate of change of temperature using Stefan's law. So why we are going to discuss now Newton's law of cooling to do the same thing? Well, the answer is when the temperature difference between the hot body and the surrounding is small, that time you can use Newton's law of cooling, because it can be shown that Stefan's law of cooling approximately becomes Newton's law of cooling when the temperature difference between the body and the surrounding is small, and it is more easier to use. So therefore, we will now discuss Newton's law of cooling. It says the energy radiated by a hot body whose temperature is T at any particular time per unit time. So again, energy radiated per unit time. So this is also equivalent to power radiated, isn't it? Radiated power, or power which is radiated at some particular time, at time t. So the power radiated at any particular time is proportional to what? Temperature difference between the body and the surrounding. Mathematically, if I write, let us write Q as the heat energy. Then dQ represents a small heat energy which is lost in time dt, and that is proportional to T minus T naught. If I put equal to, a constant will come. That constant, let me write as K. Now this heat which is lost can be written as mass into specific heat into change in temperature. But now I am waiting for a very small time interval dt. So this change in temperature also will be very small. But I must put a minus sign because this temperature decreases with time. So dt is equals to k T minus T naught, right? Which I can further write dt by d small t with including the minus sign is equal to k divided by ms T minus T naught. Now if you look carefully, this is the slope of temperature versus time graph, isn't it? Dy by dx, many times I have discussed, dy by dx represents slope of yx graph, right? So this is slope of temperature versus time graph. If I put this minus here, then it's very clear the slope is negative. So the slope is negative means the angle made with the x-axis will be obtuse angle. Also notice the slope is not constant because with time we all know this temperature decreases, isn't it? The body is cooling. So as the body cools, temperature decreases. So this difference will also decrease, right? So remember, with time, the right hand side is decreasing. So the slope is also decreasing. So the slope is decreasing, but it is negative, right? So how will a graph look if the slope is decreasing and it is negative? Here I am plotting on y-axis temperature, on x-axis time, and I know the slope should decrease. Slope should decrease means from vertical it should become horizontal, but it should have negative slope. So the angle made should be obtuse. So clearly the graph should be like this because it should start from vertical and go to horizontal, right? So it should go from vertical to horizontal. At the same time, if you draw tangent anywhere, then you can see it makes obtuse angle, right? So this is how the graph will look when you plot temperature versus time graph. It will decrease exponentially, okay? Let us now see a graphical question based on Newton's law of cooling. So the graph below, this graph shows the temperature variation. So how temperature decreases of two bodies A and B. Which body has more specific heat if all other factors are same? So keeping other things same, which one will have more specific heat, they are asking. So if you observe the graph, which graph looks more vertical? Obviously graph B, right? Graph A is more horizontal, graph B is more vertical. So therefore the slope of B will be greater than the slope of A, right? Now starting temperature is same, so T is same. Also surrounding temperature will be same, so this is same. From this formula we can see the slope of temperature versus time graph is inversely proportional to mass and specific heat. But here mass is same, so specific heat will be more for that body which has less slope. Which has less slope. A has less slope, so specific heat of A will be more. So specific heat of A is greater than B. That would be the answer of this question, right? So we have written this as Newton's law of cooling, right? So now let us say the body remains constant. So if the body remains constant, if you don't go from one body to another body, then this part will be constant, right? Mass of the body will be constant, specific heat of the body will be constant. And from Stefan's law, we know this K will contain, K will contain area of the body, right? Emissivity of the body. But as long as the body remains same, even this K will be constant. So let us write this whole thing as some constant C. Okay, so T minus T naught and minus dt by d small t. Now, this T represents what? Temperature of the body during this small interval. Now this interval is so small that you can assume the temperature to be one temperature T. But if let us say I say temperature of the body decreases from T1 to T2 in time T. So from time 0, this is temperature at time 0 and this is temperature at time T. And this T is not very small, let's say it's 5 minutes. Now in that interval of 5 minutes, T will not remain same number, right? Temperature will decrease from T1 to T2. Then how will we modify this formula? So look carefully. So let's say the body's temperature decreases from T1 to T2 in time, not is time, in time T. So this left side, what does this dt represents? It represents a small change in temperature. In this case, the change in temperature, change is always final minus initial, remember. So left side will become minus. In the numerator, this is change in temperature. So T2 minus T1 divided by this dt represents the time taken. So from here 0 to T, time taken is T, some constant. Now this capital T, what am I going to write? Remember, in small interval of time, this capital T can be taken as one number. But in this interval from 0 to T, I cannot write T1 or T2 because temperature changes from T1 to T2. So what will I write for temperature of the body? Well, I will write the average temperature. T1 plus T2 divided by 2, remember. So this T will become average temperature when the interval is large, okay, like this T. Then minus T naught. Surrounding temperature can be taken constant because surrounding is huge, right? So since surrounding is so huge, if you burn a candle, don't expect the surrounding temperature to change too much, right? So this formula we are going to use. Then what I will do, I will take this minus sign inside. So if I take this minus sign inside, this will become plus, right? So this will become minus and this will become plus, and then I will write T1 first. So I will write T1 first and then minus T2. So this way if I write, T1 will be the bigger temperature, T2 will be the smaller temperature. So this formula you need to remember in order to apply Newton's law of cooling to problems where they mention like this. Okay, we will see one example. The next question has come in previous JE question. It's asking, in 5 minutes, a body cools from 75 degrees Celsius to 65 degrees Celsius at room temperature 25 degrees Celsius. The temperature of the body at the end of next 5 minutes is. So here is the question. It says in the first case, temperature decreases from 75 to 65 in 5 minutes. So time taken is 5 minutes. In the surrounding temperature remains constant, 25 degrees Celsius. They're asking you what will be the temperature at the end. That's why I wrote T2. So at the end of next 5 minutes. Next 5 minutes from here, remember. Okay. So basically they are saying at time 0, temperature was 75. After time 5 minutes, temperature is 65. What is the temperature in the next 5 minutes means when time is 10 minutes, right? So this temperature they are asking. So this way also you can think. Now let us write Newton's law of cooling for the first case. So how I told you to write, when the time intervals are not very small but big, then I should write bigger temperature minus smaller temperature divided by time taken is equal to some constant temperature difference we should write, right? Body and surrounding. But in this interval, temperature changes from T1 to T2. So which temperature to write? Which temperature to write? Average temperature. T1 plus T2 divided by 2 minus T1. So let's calculate this. So 75 minus 65 will be 10. Time taken is 5 minutes. So let me write as 5. Some constant, this will be 75 plus 65. If you add, what will you get? 5 plus 5, 10, 0, 1 carry, 6 plus 7, 13 plus 1, 14. So 140 by 2 will be 70 minus 25. So that will give you 2 is equal to C into 5. Then it will be 6 minus 2, 4, right? So C will be 2 divided by 45. So this constant we found. Now let us go for the second case. Now for second case we can write from 75 to T, or we can write from 65 to T also. Let us write from 65 to T. So for the second case, your starting temperature is 65 and your second temperature we have to calculate. And time taken from here to here, remember, next 5 minutes they told. So from 5 minutes to 10 minutes, time taken will be 5 minutes, right? So let's try to do how much it comes. So it will be final bigger temperature, not final, bigger temperature minus smaller temperature divided by time taken is equal to constant, then average temperature 65 plus T2 divided by 2 minus surrounding, right? So this we have to simplify now, right? This equation we need to simplify. So let's put this C equal to 2 by 45 in this equation. So I'll get 65 minus T2 by 5 equals to C. Sorry, I have to substitute 2 by 45. 65 plus T2 divided by 2 minus T0 was 25. So 5 9s I can write, isn't it? Then if I cross multiply, it will be 9 5s are 45, 5 4 carry, 9 6s are 54, 54 plus 4, 58, right? Minus 9 T2. So what I did, I multiplied, cross multiplied 9 with this number, then this T2. Then here 9 went here, then 2 let me multiply with this. So when I multiply 2 with this 2 and this 2 will cancel. So 65 plus T2 minus 2 into 25 will be 50. 65 minus 50 will be 15. That 15 let me bring this side. So 585 minus 15 and minus 9 T2 let me take this side. So minus 9 T2 will go here. With this T2 it will become 10 T2. Subtract this, you get 0 7 5 equal to 10 T2. So T2 will be 570 by 10. So you will get 57 degree Celsius, right? Let's see a very interesting question where first PU concept is combined with either you can say class 10 concept or class 12 concept. So it says a copper sphere is maintained at 500 Kelvin temperature by connecting it to a battery of EMF 100 volt. The surrounding temperature is 300 Kelvin. When half the surface of the copper sphere is completely blackened so that the surface behaves like a black body, a cell of EMF 141 volt is needed to maintain its temperature at 500 Kelvin. Calculate the emissivity of the copper surface. So this diagram explains the question. We have a copper surface body whose emissivity we have to calculate. Its temperature is maintained at 500 Kelvin by applying a battery whose EMF or voltage is 100 volt. Then what they have done, one half of the surface is blackened so that it behaves like black body. Once it behaves like black body, its emissivity will be 1. And this is copper surface, so emissivity will be same, EE. But to maintain the temperature of this body at 500, we need to apply a different voltage. How much? 141 volt. So all this is mentioned in the question. Now think why the temperature of the body is maintained. Because this is cold than this. So this should lose heat through radiation and it should cool down. So why its temperature is maintained? Because this battery is supplying heat. So whatever battery will supply, so the heat or the power consumed from battery, that must equal power lost through radiation, isn't it? So whatever power it consumes, if the body loses the same power, meaning whatever energy it consumes per second, remember power is energy per second. So whatever energy it consumes per second, if it loses per second, then the temperature of the body will be maintained, right? So what is the power consumed by the body when you apply a voltage? If the body has resistance R, then the power consumed is V square by R. So in the first case, we will write V1 square by R. Resistance will be same, equals to power lost through radiation. That is Stefan's law. So emissivity is E, area is capital A, let's say, then temperature power 4 minus T0 power 4. So this is for the first case. Let me write here first case. Then in the second case, how things will change? Well, the voltage has changed, so it will be V2 square by R is the power consumed, power lost. Now here 1/2 has emissivity E, so E by E will be E and this area will be A by 2, isn't it? So emissivity into area we have to do. 1/2 has emissivity E, area is A by 2. Second half has emissivity 1 and area is A by 2 times temperature is same, this T, so this is also T, minus T0 power 4. So the best way to solve this is by dividing the two equations, because you know R is same, so when you divide R will cancel, this will also cancel, right? So what we will get when you divide this by this, you will get in the numerator V1 square by V2 square equals to E into A divided by E into A by 2 plus A by 2. Now V1 in the first case was 100 volt and V2 in the second case was 141 whole square, right? Now if you see A, you can take common from here, so A will cancel, so E divided by E by 2 plus 1 by 2, right? A smarter way to solve this is 141 can be written as root 2 into 100, because root 2 is approximately 1.41, right? So if you multiply 1.41 with 100, you will get 141. So try to remember such tricks, it will be very useful. So whole square will be equal to E divided by E by 2 plus half. So this 100 and 100 cancels, 1 by root 2 whole square will be 1 by 2 E by 2 plus half. Now you cross multiply, this into 1 will be E by 2 plus half equals to multiply 2 with E, 2E. So if you take E by 2 this side, 2E minus E by 2 will be E common, right? E common, 2 minus half, LCM 2, 4 minus 1, 3, 1 by 2, 2 cancel, so E will be 1 by 3.